we have to test the continuity and the existence of partial derivative of a function at the origin. The given function is f of xy equal to x square y divided by x to the power 4 plus y square when xy both are non-zero and the function value is 0 at the origin. First of all, to test the continuity at the origin, we have to find the limit of this function at the origin. Here you can see in both numerator and denominator the power of x is twice that of y. In this case, we approach the origin along y equal to mx square, and you can see here as x tends to 0, y also tends to 0. Now if we choose this path and evaluate the limit, we will have limit of the function x square into mx square whole divided by x to the power 4 plus m square x to the power 4. After simplifying, we have m by 1 plus m square, which is different for different values of m. So you can see here limit of the function at the origin does not exist. We can say the function is not continuous at the origin. Now let us check the existence of partial derivatives. Thereat you can easily verify that both the partial derivatives exist at the origin. So the first order partial derivative of f with respect to x at the point 0, 0 is evaluated using this limit. You can see simply here the limit exists and equal to 0. Similarly, the partial derivative of f with respect to y at the origin is also equal to 0. So we can conclude here that the given function is not continuous at the origin. However, it possesses first order partial derivatives thereat. So here no given option is correct. Also you can see here option A and option B both are the same, and in option C it is given f is continuous, which is not wrong. In option D it is given that f is not continuous at the origin and one partial derivative of f does not exist. It is also wrong, so no given option is correct. In question number 36, we have to find the direction in which the directional derivative of the given scalar function f of x, y, z, which is equal to xy plus yz plus zx at the point 1, 2, 3 is 0. You know that for a differentiable function f, its directional derivative at a point a in the direction of a vector u is given by the dot product of gradient vector evaluated at a and the vector which represents the direction, that is the directional derivative is nothing but grad f at a dot the direction vector u. In this question we have f of x, y, z is xy plus yz plus zx. Then the gradient of this function is defined by fx I cap plus fy j cap plus fz k cap. Basically the components of the gradient vector are the first order partial derivatives of f with respect to x, y and z. So you can see to find the gradient we have to calculate the first order partial derivative of f with respect to x, which is y plus z. Similarly fy is x plus z, fz is x plus y. After finding the gradient vector, we have to evaluate the value at the point 1, 2, 3. So the gradient vector at the point 1, 2, 3 is 5 I cap plus 4 j cap plus 3 k cap. Now to find in which direction the directional derivative is 0, we have to find the vector which is orthogonal to the gradient vector at the given point. That is, we have to find the vector which is orthogonal to the vector 5 I cap plus 4 j cap plus 3 k cap. So for that we have to take the dot product of the gradient vector and the vectors given in option A, B, C and D. You can see here, if we take the dot product of the gradient vector evaluated at 1, 2, 3 and the vector given in option C, that is I cap plus j cap minus 3 k cap, we get 0. So the directional derivative of the given function at the point 1, 2, 3 is 0 in the direction of the vector which is given in option C, that is I cap plus j cap minus 3 k cap. So option C is correct. In question number 37, a function of two variables is given to us, which is 3x minus x to the power 3 minus 2 into y to the power 2 plus y to the power 4. We have to classify the stationary points of this given function. You know, to find the stationary points we have to solve the equations fx equal to 0 and fy equal to 0. Fx is the usual notation for the partial derivative of f with respect to x. Similarly, fy means the partial derivative of f with respect to the variable y. So to find the stationary points, we have to calculate the first order partial derivatives of f here. Fx, you know, the partial derivative of f with respect to x, it is 3 minus 3 into x to the power 2. Similarly, we calculate fy, which is 4 into y to the power 3 minus 4 into y. Now we need to solve the equations fx equal to 0 and fy equal to 0 to obtain the stationary points of the given function. Fx equal to 0 means 3 minus 3x square equal to 0 gives us x equal to plus or minus 1. Similarly, the equation fy equal to 0 gives us y equal to 0 or y equal to plus or minus 1. Now you can see here there are 6 stationary points, minus 1, minus 1, minus 1, 0, etc. To classify the stationary points, we need to check the sign of AC minus B square, where A is the second order partial derivative of f with respect to x, B is mixed partial derivative of second order, and C is the second order partial derivative of f with respect to y. If AC minus B square is greater than 0 at a considered stationary point, then the stationary point is an extreme point. If AC minus B square is less than 0, then the stationary point is a saddle point. If AC minus B square equal to 0, then the test is inconclusive and further inspection is required. So first of all, let us consider the stationary point minus 1, minus 1. At this point, we have to check the sign of AC minus B square. So let us first calculate what is the value of A. A is minus 6x here. So at the point minus 1, minus 1, A is minus 6 into minus 1, which is 6. B is the mixed partial derivative of second order, which is 0. So it is 0 here. C is the value of second order partial derivative of f with respect to y at the considered stationary point, that is minus 1, minus 1. So here we put y equal to minus 1 and there is no x term, so we get 8. Now you can see AC minus B square is 48, which is greater than 0. Since AC minus B square is greater than 0, so the point minus 1, minus 1 is an extreme point. Now you can check the sign of A or C. A is greater than 0, so the function has a local minimum at the stationary point minus 1, minus 1. Similarly, you can check that AC minus B square is greater than 0 and A is greater than 0 at the stationary point minus 1, 1. So this point is also another local minimum point of the function f, or f has a local minimum value. Similarly, you can check the function has a local maximum at the point 1, 0, and the other 3 points minus 1, 0, 1, minus 1 and 1, 1 are saddle points because the value of AC minus B square is less than 0. So here I think option D is the best possible option. Let us discuss the solution of question number 38. Here a vector r is given to us, which is the standard position vector in R3. R vector is xi cap plus yj cap plus zk cap, and you know r square is the dot product of r vector with itself, which is x square plus y square plus z square. So r is square root of x square plus y square plus z square. Among the given options, we have to find which option is false. So in option A, we have to calculate Laplacian of 1 by r, that is Laplacian of x square plus y square plus z square whole to the power minus half. And in option B, we have to calculate gradient of r square. In option C, we have to calculate the divergence of r vector. And in the last option, we have to calculate curl of the vector r. The calculation of Laplacian of 1 by r may take more time than calculating the gradient of r square, divergence of the vector r and curl of the vector r. So let us start with calculating gradient of r square, that is with the option B. So r square is x square plus y square plus z square. You know that the gradient of a differentiable scalar function is a vector whose components are the partial derivatives, means the first order partial derivatives. So here you can see gradient of x square plus y square plus z square. It is the partial derivative of x square plus y square plus z square with respect to x, that is 2x I cap, plus the partial derivative of x square plus y square plus z square with respect to y, that is 2yj cap, and the partial derivative with respect to z, which is 2z k cap. So gradient of r square, that is x square plus y square plus z square, is 2x I cap plus 2yj cap plus 2z k cap, which is 2 into r vector. So option B is true. Let us move to the option C. So where we have to calculate the divergence of r vector. Divergence of any vector v, it is written as the nabla operator or del operator, del dot v, and curl of any vector v is nabla cross v vector. So here to calculate the divergence, so we have to calculate the dot product of nabla and the r vector. You can see if you take the dot product, we have the partial derivative of x with respect to x plus partial derivative of y with respect to y plus partial derivative of z with respect to z, so which is 1 plus 1 plus 1, which is equal to 3. So option C is also true. Now we calculate curl of r. Gradient of r square is 2r vector, 2 times of r vector. So r vector is nothing but gradient of r square by 2. And you know that for any differentiable function f, curl of gradient of f is 0. So here curl of r means curl of gradient of r square by 2, which is 0. Or you can use the formula, that is curl of vector r is here nabla cross r, and you can find the value of this determinant, which is 0 vector. So option D is also true. Note that when we say the divergence of a vector v is the dot product of del and v, that is del dot v. So here it is technically not the dot product. Similarly, the curl of vector v is del cross v. Here also it is not the cross product technically. If we calculate the Laplacian of 1 by r, that is Laplacian of x square plus y square plus z square to the power minus half, we get 0 for any differentiable function f. Its Laplacian is fxx plus fyy plus fzz. To calculate the Laplacian of 1 by r, that is x square plus y square plus z square to the power minus half, we have to calculate the second order partial derivatives with respect to x, y and z. After calculating, if you add these three terms, you will get 0. Alternatively, you can use this method to show Laplacian of 1 by r is 0, or you can use Laplacian operator in spherical coordinates to show that Laplacian of 1 by r is 0. So here you can see the statement given in option A is false. We have to choose option A.